So this is the lecture 24. In this lecture, we're gonna talk about the failure and the strength, and the later part we will talk about the stresses in the material. So then, what is the failure? So what would be the failure when we consider the failure? Failure is very subjective concept. Let's say that we have some kind of a slope like this, and we are building a structure, so it has a foundation like this, and it applies the stress. Right? And as we increase the stress increases, then it will deform a little bit by a little bit, and then eventually it's gonna slide, right? So then, for example, when the sigma is very low, the movement of this foundation will be very slow and very small. So if this structure is built in the middle of nowhere, like in the mountainous area where nobody is living there, and if the slope failed, it wouldn't cause any damage to the society, right? So then we can accept large deformation, right? Can we call it a failure? But on the other hand, if this foundation supports the nuclear reactor, and if we have the deformation of the soil mass or ground by maybe like 0.1 millimeter, 100 micrometer. So the foundation has moved by 100 micrometer. And if it affects the functionality of the nucleosilo or nuclear reactor, then we can call it the failure. So then when the deformation becomes here, this term, unacceptably large, we consider it as the failure. So this acceptance of the deformation can differ from structure to structure. Right? So if it's the bridge, then you may allow 10 centimeter deformation. Still, if the vehicle can transpass. If it's the very sensitive structure, like a nuclear silo or some factory machine with the semiconductor fabrication, then the 1 millimeter deformation can cause can damage the functionality of the machine. Okay, so the failure is each structure type, depending on the structure type, the allowable deformation is different. So then, what is the strength? Strength is maximum or ultimate stress that the material can sustain without failure. So this is also the subjective term. Huh? So strength, sometimes if you only allow very minute deformation, then the strength can be estimated very low. If you allow the large deformation, then the strength can be large. If you think about the rubber, what is the strength of the rubber, right? When it can deform maybe 1 millimeter, then it's gonna be the strength it can sustain will be very small. Right? We have a rubber band, and then if it can hold the force and without a failure, even though it stretches 1 meter, then the strength will be large. Yeah? So then can we predict? So and then when we think about this, back to this slope and failure, when you slide along this failure envelope, then when you look at this soil mass, in soil mass, soil has sheared. It failed by the shear. So then here you have vertical stress and the horizontal stress, and this will determine the strength of the soil and whether it can resist sustain the applied load, applied stress. So as you can see from this example, soil undergoes shear failure in most cases. So shear stress and the shear strength determines the failure. And shear strength is the maximum shear stress that the soil can sustain without the failure. When you look at this soil mass, so this is the soil mass, and you have a vertical stress and the horizontal stress, and this is the failure plane. And on that failure plane, you have a normal stress that's compressing, and you have a shear stress tau that's shearing the material, or causing the sliding between the grains. Okay, then we'll talk about the principal stress. So if you have taken the materials of mechanics class or the solid mechanics, then you will be familiar with this principal stress and the principal plane. Stresses are defined on a plane, right? Because the force has a direction and the magnitude, that's a vector, right? So stresses also have the direction and the magnitude. So it acts on the plane. This is different from the pressure. Pressure doesn't have the direction, right? It's a scalar. But stress a vector or tensor in 3D. So then at a certain depth, when you think about the soil mass, that's a square cube or the cube, you will have a vertical stress and the horizontal stress and another horizontal stress. So H1 and H2. It's called the true triaxial stress condition. And in most cases, sigma H1 is almost the same with the sigma H2. So we can simplify this one into this kind of cylindrical soil mass with the sigma V and radial stress sigma H or sigma R. So this is kind of a simplified condition from the true triaxial stress condition when the sigma 1 is similar to sigma 2. Sigma H1 is similar to sigma H2. Okay. So here, before we move forward, we have to have some certain rule for the sign convention. In geotechnical engineering, the normal stress is positive when it's compression. So it's not about the direction, whether it's aligned with the gravitational direction or not. No? So it's about the if it's compression, then it's positive, and if it's tension, then it's negative. And the shear stress is when you think about this mass, which is just the part of the soil mass that's cut off. Then you have a string that's holding this object. So the object is in a kind of pendulum stage, and it can go back and forth by the force. And if the shear stress tau is swing in clockwise direction, then shear stress is positive. Clockwise. So if the shear stress causes the clockwise swing in this pendulum, then it's positive. Counterclockwise is negative. Okay, principal planes. Principal plane. Principal plane is defined as a plane with zero shear stress. And principal stress is defined as the normal stress acting on a principal plane. So if the shear stress is zero here, maybe you can hear. If the shear stress is zero here, tau is zero, then the normal stress here, this will be the principal stress. And principal plane will be this one. Right? And in 3D world here, we have three principal stresses, sigma 1 and sigma 2 and sigma 3. They are orthogonal on each other, right? So the biggest one is called the major principal stress, and the smallest one is called the minor principal stress, and in between, that's intermediate principal stress. So in soil, when you have a soil cube like this, sigma V and sigma H1 and sigma H2, and sigma H1 is generally the same as the sigma H2, then it can be like this. And in 2D world, we can simplify this one into a square with the sigma V and the sigma H. If there's no shear stress on this horizontal plane, then this plane will be principal plane. And if there's no shear stress on this plane, then this vertical plane will be principal plane. Okay. In the next page, let's think about one soil mass, and major principal stress sigma 1 is applied on the horizontal plane, and sigma 3, that's minor principal stress, is applied on a vertical plane. Then here we are looking at this plane. We are cutting the object with this line, and then there will be a normal stress acting on this plane of interest, and there will be shear stress acting on this plane, right? So then sigma theta and tau theta can be obtained using this equation. Sigma theta will be sigma 1 times cosine square theta plus sigma 3 times sine square theta. And tau theta will be sigma 1 minus sigma 3 sine theta times cosine theta. And here the theta is measured counterclockwise from the direction of sigma 1 to the direction of sigma theta. So then it means that theta is measured counterclockwise from the direction of sigma 1. So this is the direction of the sigma 1, right? And theta 1 direction is this, right? Because this is the one. Then counterclockwise is this direction. This will be the theta. Fortunately, here the theta is the same as this here. But in some cases, it's not the same. Okay, because we have these two equations to get the sigma theta, which is normal stress acting on the plane of interest, and the tau theta, the shear stress. Using these two equations, we can draw a circle in a sigma and tau space. So x-axis is the sigma and the y-axis is the tau. Then sigma 3 and sigma 1, you can draw a circle. And here's the center. So because this point where the major principal stress sigma 1 is applied, shear stress will be 0 because that's the definition of the major principal stress. Principal stress. Sigma 3 also here. So principal stress will be located on the x-axis where the y value is 0. So then the distance here, the location of the C, the center, is called the center of the circle, and that's sigma 1 plus sigma 3 over 2. And the radius, which is this one, will be sigma 1 minus sigma 3 over 2. Right? So radius of the circle. And A and B, this is the A, point A, and this is point B. And the length of the distance between A and B, the length between the A and B is sigma 1 minus sigma 3, and that's called the deviatory stress or difference in principal stresses. So using these two equations or using this Mohr circle, you can identify, you can draw a circle, right, for given sigma 1, sigma 3, and you can find the normal stress and the shear stress on any plane. That means that the point along this on this circle represents the stress state on a certain plane. For example, here, right, it will have a normal stress of this much and this much, and sigma theta and tau theta, it will represent the normal stress and the shear stress on a certain plane. And for a given sigma theta and tau theta on any two planes, sigma 1 and sigma 3 can be also major principal stress and minor principal stresses can be determined using the Mohr method. Okay, then to find out the more details and the mechanism of the Mohr circle, let's look at the Mohr method here. Mohr method is this is very convenient way to interpret the Mohr circle and find the stress state for on the plane of interest, or any plane that you're interested in. Okay, let's go one by one. These are the steps to find the stress state, and step 1 is to find the pole, which is also referred to as origin of planes, OP. To find the pole, draw a line from a known stress. This should be a known stress point parallel to the plane upon which the known stress acts. So that means that here, this is the soil mass with the known stress condition. So we know the sigma 1 and sigma 3. Sigma 1 is vertically applied, and the sigma 3 is now applying on the horizontal, the vertical plane horizontally. So then we can draw the circle using the sigma 1 and sigma 3. So here the coordination will be sigma 1, 0, and here sigma 3, 0 will be the coordination. And we want to find, okay, so let's find the pole, right? So pole is sigma 3 is here, right? And sigma 3, the minor principal stress, is acting on the vertical plane. So if you draw the line parallel to this vertical plane, the intersection with the circle is the pole. So this will be the pole. Pole is a point on a circle. We can find the pole from the sigma 1. Sigma 1 is here, right? And sigma 1 is acting on the horizontal plane. So then maybe I can use the different color. Here, if we draw it horizontally, then this will be the pole, right? Okay, so then second, find the state of stress acting on the plane of interest. So okay, let's assume that we are interested in stress on this plane. So we want to find the sigma theta and tau theta acting on this plane. So then, actually, if we can plot it differently, I can take the bottom half only, and this is the theta. And we want to find the sigma theta and the tau theta. This one. Okay, then draw a line through the OP and parallel to the plane of interest. So this is the plane of interest, and parallelly you can draw a line. And this will have the theta. So then intersection with the Mohr circle represents the state of stress inclined at the same orientation. So here, intersection with the Mohr circle, sigma theta, comma, tau theta will represent the stress state on this inclined plane of interest. So let's look at this example here. So sigma 1 is given 52 kilopascal and sigma 3 is given 12 kilopascal. Then you can draw a circle, right? 52, 0 and 12, 0. Then we want to find the sigma theta and tau theta on this plane of interest. That's in the red line. Then we can draw because we have to find the pole first. The pole will be here. Because if you draw the line parallel to the plane that sigma 3 is acting on, then this will be the intersection with the pole, with the circle. So this is the OP, the pole. And then you can draw the line parallel to, it's already drawn here. Then this intersection will give you the sigma theta and tau theta. Right? So, and here it's about 35 degree. It's about 35 degree. And because you know this angle, then you can find the sigma theta and tau theta trigonometric relation here, right? You know the center and the radius and the angles. And if you compare it, you get 39 kilopascal as the normal stress, and shear stress will be 8.6 kilopascal. Okay, that's it. So in the classroom, in the class, we're gonna have more example to explore this pole method together. Thank you.